a better word for that we've introduced here in our waves topic would be oscillating, right? So hopefully what we're going to aim to do today is we're going to aim to discuss what we mean by an oscillation, right? What we mean by oscillations, and also how oscillations that we create here in the video game and the simulation can compare to stuff in the real world. And if you manage to measure and graph oscillations, that would be wonderful. So let's talk about what oscillations actually are. And we'll use our little cube up there, which I'll just go get, to demonstrate an oscillation. So let me zip over there. Whoop, I'm silly. Let me zip over there. Down I go. Woo! Okay, so the conservation of momentum's flown me over there, and I grab this cube. Wonderful. So I'm going to set up a portal here, and I'm going to put a portal right underneath our cube. Wonderful. And then our cube is just going to bounce up and down there. It's kind of grating on the sides, but that's actually interesting. We can talk about that in a second. So, what we have here is whenever we drop an object into the portal, right, it comes out upwards from the other portal. Then the object reaches its maximum height. Oh, it got stuck. Let's get our cube out of the way. And eventually it reaches its maximum height, starts falling, and eventually comes back upward from the original portal. It's like bouncing off the floor, except you turn upside down each time you bounce. So here I go. Oh, let's see if I can create an oscillation. There we go. So I'm just oscillating up and down, up and down. I enter feet first, I exit, my feet coming out first, I gain my maximum height upside down, I fall back into the hole, and then I reach my maximum height the right way up. I'm oscillating up and down, up and down, up and down. So, when something's moving repeatedly up and down or backwards and forwards, we say it's oscillating. So I was oscillating there in the portal, right? And the object that oscillates it is the oscillator. So I was oscillating, yeah? I was oscillating, and the portal system was the oscillator, right? So, we can think of other examples in the real world. A pendulum, yeah? That would be something that would be oscillating backwards and forwards. A girl on a swing, that would be an oscillator system, right? The girl on the swing going backwards and forwards. And in this case, the thing that's actually oscillating, well, that's the girl. Oscillation is one of the most basic processes in the universe, right? So from piano strings strumming, as we've done in a previous video, to tree branches in the wind, even stars in the galaxy, so many things in nature oscillate, right? So the time it takes for something to get back to its original position is called the period of the oscillation. So the time it takes for me to be the right way up again, yeah, just like when I originally jumped into the portal, would be the period of my oscillation. So let's go back to our system here, and what we can actually do is we can work out the period of the oscillation of our cube here, right? So let's pick up the cube again, and let's drop it into our oscillator and let it start oscillating just like a wave, oscillating backwards and forwards, backwards and forwards. So anything that's oscillating, whether it's a wave, like we've looked at in our examples in the past, or whether it's this oscillating system here with the cube oscillating upwards and downwards, we can work out that period, right? The period would be how long it takes the cube to do one full oscillation. So, starts up here, ends there. One period. One period. Period starts, period ends. Yeah? So that whole motion of going back to the start would be known as one period. Now I'm going to grab a stopwatch here, and you can do the same thing. You could grab your phone or something like that, and we're going to measure the one period of this system. Now my recommendation, the best way to do this is to actually take 10. If we record 10 oscillations here, then we can divide that by 10 and get an average. So that's going to help reduce the amount of error we have due to our human reaction time. So I'm going to start this clock. You can do your own and correct it and use your reading if you prefer it, or you could even slow down on the video to get a much better reading and then account for that when you're taking your time. So I'm going to try and start this in 10. Go. 1. Oh, I didn't start my stopwatch. Go. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10 oscillations. Okay, so I got 14.8 seconds. So that means what we're looking at there is we must, if 10 oscillations was 14.8, that means that one oscillation is divided by 10 of that. 14.8 divided by 10, well, that gives us 1.48 seconds for the time period of our oscillating system. Yeah? So 1 would be 1.48 seconds. That is the time period of this. Now, something else you can do is you can actually work out the frequency of that. If you take the time period, yeah, and you do 1 divided by the time period, you can actually work out the frequency. Yeah? Because if we know that one oscillation is 1.48 seconds, we can do 1 divided by 1.48 seconds to find out how many, waves there are per second. So 1 divided 1.48, 0.68 waves per second, 0.68 hertz. So that's something else you can do a little bit advanced, where you can take the actual time period, and change that over, yeah, now into a frequency. We can think about things that might actually change, the time period. Maybe if we introduce some friction. Yeah? So if we've got some friction of me, or it's grinding against the sides there, that's going to affect our time period, and even to a point where it stops it altogether. Yeah? But the key thing I want you to take away from this lesson is what an oscillation is. It's something moving backwards and forwards. What an oscillator is, it's a system that results in oscillation. And also what we mean by the period of oscillation, or the time period. Well, that's how long it takes for one wave to pass in seconds. And we've got a really nice method of doing that. We take 10 oscillations and divide it by 10 to try and reduce that human error. Yeah? So hopefully we've learned a little bit more about oscillations and bouncing up and down, and how that relates to our waves.